this, I mean, you had to do something like this for that moles assignment, but are the following things soluble? What type of reactions are these? Balance them. Predict the products of one. That might change to both. Double replacement reactions. Be sure to indicate states. So one should be a solid, one shouldn't. And then there's a couple that are a little bit more fun to balance, which it's got marks associated, and it would be a little bit more tricky if you didn't have Google sitting beside you when you did it, but I mean, that's neither here nor there. So are these three things soluble? So we have on the back of our periodic table this solubility of some common ionic compounds in water, blah, blah, blah. So other than, I thought I had a pen. Other than those three positive ions, you have to base it on the anion in the ionic compound. So here I have calcium carbonate and potassium carbonate, which are two fairly common things. If you've ever seen or had Tums, the active ingredient in Tums is potassium or calcium carbonate, and in theory you could use that as the same idea. They both have carbonate, so we need to go over to the carbonate aisle column. So this is for carbonate, phosphate, and sulfite, but they all, in general, behave the same. So calcium, these four plus lithium carbonate, I would probably put lithium carbonate up here, but then I didn't build it. Hydrogen with those is soluble. Sodium, potassium with those is soluble. So potassium carbonate should be yes. Ammonium is there. So calcium is not part of that group. So that's a big old no. Is that bit. And then cadmium chlorate. Well, chlorate is kind of covered under here. I guess if I hold the eraser, it kind of circles it. So it says most, and it's got some exceptions. There's no chlorates that are exceptions, so you would have to assume that that is also a yes. So it's just above the line is yes, below the line is no. So this was the summary page. And a chemical equation describes a reaction. We have to have the conservation of mass, which means we have to balance it with coefficients. Yeah, there's some symbols. 5 types. Formation, decomposition, single and double replacements, and combustion. We identify them all generally based on the reactants. So if you're looking to predict products, determine the type of reaction you're looking at. Put the pieces together. If it's formation, you're putting two elements together, making a compound. If it's decomposition, there's a couple decomposition ones on there that I put what actually happens. If you put it into the elements, that's fine. Single replacement, you're switching a metal with a metal, a non-metal with a non-metal. Double replacement, look at charges. So, and I'm going to go through a couple more of those with, what's the word I'm looking for? Precipitates. Combustion is C something, H something, generally plus O2, and usually CO2 and H2O. So I think on that test there's basically, well, there used to be one of each, but I can't remember what it is. And then we balance with coefficients. So I did all of those. If I look at this one, silver nitrate is Ag and NO3, zinc chloride. This is +1. This is -1. +2, -1. So I'm going to take the positive from this one and it's going to make a compound with the negative chloride. Well, I've got +1 and -1, so that gives me AgCl. And then the +2 and the -1 there gives me Zn, 2+, so that's, I need 2 NO3s. Once I have my formulas written, then I balance. Well, I've got 2 chloride here, I need 2 chloride there, which means I have 2 silver, I need 2 silver, which everything kind of works out. And I think those are all balanced. If they're not there now, I will put those up shortly. Or well, when we're done. These ones were a little bit more straightforward because you have the stuff, a formation reaction. Magnesium plus oxygen gives magnesium oxide. That's a single replacement because an element and a compound. Double replacement. One thing and an arrow is decomposition. And combustion. So those are all balanced. These ones with the chlorates make magnesium chloride and oxygen, technically. Calcium, oh, there was one other one. Calcium oxide. Oh, it must have been on the other page. Calcium oxide and water makes calcium hydroxide. That's not one that you would have to know specifically. Like, I'm not going to give you an equation that you wouldn't be able to do with the tools I've taught you. Sorts of old blank pages. All right, so we still have. So if I take solutions of those two things and I react them together, I'm going to go through a couple of these old ones and whether they're on there or not. If these are aqueous, well, silver is a +1 ion. Nitrate is a -1 ion. Sodium is +1. There's 2 of them. That's -2. So these 4 are all double replacements. So I take the positive part here and go with the negative part there. So +1 and -2. I need 2 +1s. And those two, well, +1 and -1. So now I'm going to balance it. Now I would probably start with silver or sodium. I see 2 sodiums here, so I need 2 sodiums there. To me, that gives me 2 nitrates, which means I need to have 2 nitrates on that side, which puts the 2 there. 2 silver, everything is good. Now, I'm just going to pull that up instead of trying to copy and paste. We have silver sulfate. So sulfate. Most sulfates are soluble. Calcium sulfate. No, we don't have that. Strontium, barium, mercury, lead 2. Oh, silver sulfate is down on the bottom. Okay, be that way. So this one has low solubility. So that's a solid. If this was all done in water, nitrate is here. There's no nitrates. All nitrates are soluble. So this would be aqueous. We can do the same thing for all of these. +1, -1, +2, -1. Ammonium nitrate goes together, +2 and -1, so I need barium chloride. 2 chlorines, 2 chlorines, 2 ammoniums, everything's balanced. If I go back to this, ammonium and nitrate are all generally soluble, so that one would be aqueous. Chloride, most, That's interesting. Because I'm like 99% sure barium chloride is insoluble, but based on those rules, that would be aqueous. +2 - 1, +1 - 2. +2 goes with the -2, so calcium sulfate. +1 and -1. Well, this one's easy to balance because I'm just going to put a 2 there because I've got 2 potassiums and 2 potassiums. We balance with a coefficient, not by saying K2Cl2 because that makes no sense. Chloride, potassium isn't down there, so that's aqueous. And then what was the other one we had? Calcium sulfate. Sulfate, most. Oh, calcium is down on the bottom. Solid. Aqueous. And quickly, well, it's +2 - 1. Anything with a nitrate and an H is soluble PbCl2. Should be Cl Pb2+. And that one's a solid. So I'm going to put an assignment that has a couple questions with those up with balancing. That kind of puts everything into place. If you want more practice, I have these ones that are in here that I found at some point last year that has products predicted. But I'm going to get rid of stuff. I can't remember which file that's in. All right, so that's the end of what we need in chapter 11. I did start chapter 12, and the first part of chapter 12, the first thing we're going to do is actually, you can sit back and watch. Chapter 12 is called stoichiometry, and it's an old, I think the word has, well, I think I have some of the roots to the word over here. Once this takes a while, it has to do with counting and stoichiometry, measuring elements. So it's a quantities. So suppose you have 2.5 grams of sodium chloride and a whole pile of silver nitrate, and you throw it in a giant pail of water. Something will happen, a solid will be produced. Can you predict how much solid is produced? Well, this section, we're going to combine, well, sodium chloride and silver nitrate. Well, that's pretty easy. That's NaCl. It's in a pail of water, so it's aqueous. Silver nitrate is not only good for vampires, it's good for chemistry, or werewolves, or whatever. Those react together. This is a double replacement reaction. +1, -1, +1, -1. So the sodium goes with the nitrate, and we have all of those are soluble, plus silver with chloride. And I can go back to my periodic table and say chloride, silver is, so this is a solid. So we're given 2.50 grams of this. We want to know how many grams of that is produced. Well, is our equation balanced? Yes. Chemistry, everything goes through one particular unit, and it's that big weird one of the mole. So if I gave you a question on that mole calculations thing, how many moles are there in 2.5 grams of sodium chloride or table salt? You go to your kitchen. How many moles of that would we have? Well, that's moles of NaCl, 22.99 grams per mole, 35, 45. So the molar mass of sodium chloride is 58.44 grams per mole. So 1 mole of sodium chloride is equivalent to 58.44 grams. And I'm putting grams in the denominator or the bottom, so grams of this can cancel with that. We can do this times 1 divided by that. Pull out our calculator. 2.5 divided by 58.44. So this gives me 0.0428 moles of sodium chloride. So that's fine, but that's not what the question asks. The question says, how much of this is left? Well, if I have one molecule of this and one molecule of that, and I mix them together, I get one molecule of this and one molecule of that. If I have 100 of these and 100 of those, I get 100 of these and 100 of those. Keep scaling. If I have Avogadro's number of these and Avogadro's number of those, we would do that. So 1 mole of that would if 1 mole of this produces 1 mole of that, and we're going to do this in a little bit simpler way, 0.0428 moles of NaCl would produce of silver chloride. And this is the essence of stoichiometry, is this step. Because it's all about moles, which is just a scaled up version of dozens or however many in total. And we're using sodium chloride because it says a lot of silver nitrate. That implies we've got more silver nitrate than we're ever going to need. And you'll see the word excess. You can think about it in terms of if you're making a sandwich and you have 8 loaves of bread and your parents shop at Costco and you have the giant, like, 3-liter bottle of mayonnaise, if that's your thing. And you have 2 pieces of ham. How many sandwiches can you make? Well, it depends on whether or not you want 1 piece of meat on the sandwich or 2, but ultimately you're limited by one of the quantities. And when we only give you the mass of 1, that's our limiting bit. We have 2.5 grams of ham. How many sandwiches can we make? So now if I know we have that many moles of silver chloride, can we add up the mass and just do the conversion back? 0.0428 moles of silver chloride. Let's move this over a little bit. Silver is 107.87 to 13 143.32. I have moles, so I want, oops, sorry. $143.32. What? Grams are in 1 mole, assuming I added that up properly, which looks reasonable. Moles cancels with moles. I can multiply that out, depending on how nerdy you are. Times 143.32 gives us, go away, 0.13 grams of silver chloride. So you have, a lot of people say, well, how can 2.5 grams produce 6 grams? Well, we have that many grams of that. We have all sorts of it. We have plenty to use. But that means we have a whole bunch of silver atoms. Does silver fundamentally weigh more than sodium? Well, yeah, by a factor of almost 5. The chloride is similar. So it's possible to start with 2.5 grams of something and end up with that many grams, because we can figure out how many grams of this we need, how many grams of that would be produced, and everything does balance out, but we're only actually concerned with the two things that were asked in the question. And that is stoichiometry in a long, kind of roundabout way. We will look at this kind of conversion, what's called a mole ratio, converting moles of something to moles of something, and then what's called gravimetric stoichiometry. Gravity involves mass, which is going from a mass of one to a mass of the other. And that's what we just did. And that's what we'll start with, and we'll get through some of that tomorrow, some of that on Tuesday. And there's one other thing, the kind of sandwich question was limiting reagent. Oh, whoa! And we'll talk quickly about yield. Limiting reagent is about excess. 14 loaves of bread, 10 pieces of ham and cheese, and a bucket of mayonnaise. How many sandwiches can you make? It's coins. You have certain things, and we'll probably go through that example, and that's about it. But that's kind of all for today. I will post an assignment shortly, and tomorrow we'll carry on with stoichiometry. Is there any questions? Either Ryan's internet is bad, and he just doesn't want to talk to me. We're good. We're good. And we'll talk to you tomorrow morning for, I think, Amy is the only one in, Alyssa's in math. She just doesn't get up early enough for math. Gosh, I can't even... somebody unmuted.
Okay.
Yeah.
You should start the chemistry classes earlier than 2 o'clock.
How come?
Because I have to wait like 4 hours for the next class. It's like my day revolves around, you know?
Okay. That's a possibility. You four are the ones who are here all the time. Do any of you guys have biology or physics? I think are the other ones that kind of do things regularly earlier.
Yeah, I have biology and physics.
What times are those?
Pardon?
What times are those?
Oh, I have biology normally at 1, and then physics normally at 11.
Oh, okay.
Tuesdays and Thursdays.
Okay. Let me think about that, and we'll try to maybe do something a little bit early. Caitlin, do you have any conflicts with earlier?
No, I don't have any other classes.
Jeez, it's like I'm the only one who's doing stuff. Maybe I should do less. I don't know. But we can try to figure a time out. Are biology and physics long? Like an hour or...
Biology is long because Mr. Ballet likes to talk.
Yeah.
Physics isn't too long. But...
Oh. Okay. Because we may be able to sneak something in, or... I mean, lunchtime isn't spectacular. I mean, I'm up early, and the kids go to the sitter at like 8 o'clock. So I mean, I can be here, but I'm not going to force somebody to get up at 9 o'clock because, oh no, 9 o'clock is like.
I'm up. Yeah, I'm up usually at like 7:30.
Okay. I will maybe post something, or one of you guys can post something and say, would anybody want to do chemistry at 9 o'clock instead of 2 o'clock, and see if other people would be more willing, because I mean the four of you are here every day, so if we can make something work for the four of you because you're here all the time, if everyone else is just watching the recording or doing whatever, well, it's tough for them. If you guys show up, I'm willing to move things to a different time to accommodate you guys, because you're the ones who are here.
Yeah, it'd just be nice to get it done and out of the way, you know?
Yeah, oh yeah, that wouldn't bother me at all.
Okay.
Okay. All right, we'll see you guys tomorrow at 2, and then we'll see where we go after that.
Okay.
Perfect.
Okay, thanks.
No problem. Thanks. You're welcome. Bye.